So, in starting off this course in discussing calculus, it's really important for us to understand what a limit is because that's really the foundation upon which calculus stands. And what a limit is effectively a way of describing the behavior of a function as x approaches a specific value. So for instance, let's say we had let's say just a function that looked like this. I'm just kind of an arbitrary function here. And we had a function that looks like this. And suppose we had just some arbitrary uh, x value, suppose that we're c. And what we're doing here is we're saying, okay, as our function approaches, or excuse me, I should say, as we approach c, some value c, as we approach the c value from both directions, what is my function doing? Specifically, how is my function behaving? What values does it look like our function is approaching? And what we could say here is, all right, as we are approaching our horizontal value of c, it looks like our function is approaching some numeric value, which we'll call L. And in terms of using limit notation, what we would say is the following. We'd say, all right, the limit of our function as we approach c, the limit of our function as we approach c, some horizontal value here, c, is this numeric value L. So a limit is a way of describing how a function is behaving by assigning it a numeric value, by saying it looks like our function is approaching this numeric value. Now, it's important for us to note that in order for a limit to exist, we need to be approaching the same value from both the left and the right side. And we will talk about that more in just a moment. I want to also highlight, as we are going through some of our discussion on limits, that there are a number of different limit properties that we can use. So we could say, for instance, that the limit as x approaches c of some function, f of x, we know is going to be equal to L. Now let me also write temporarily, I'll just kind of write this on the side as well. The limit as x approaches c, let's just say actually not f of x, let's use a different function, g of x. Let's say the limit of that function as x approaches c, we're going to call this m. Well, going back to this, we can say the limit, suppose, of f of x plus g of x. So suppose we're finding the limit of the sum of these two functions. Now, sometimes it might be a little bit of a headache to try to add up two functions and see what the limit is as x approaches c. So there are certain limit properties that we can use here and say, all right, well, in this instance, we can actually just find the limit of f of x as x approaches c, and then find the limit of g of x, which we said was m, and then just add those two results together. So there are a number of different limit properties that we can use. So as we continue this, we can say, all right, what about when f of x is, if we're subtracting g of x from f of x, in this case, we would say the L minus m, f of x times g of x, we would say is L times m, f of x, let's just say divided by g of x. Well, this would be L divided by m. And even when we have scalars, like some scalar value like k times f of x, well, that would be the same thing as just multiplying that scalar times that limit. So just a couple of things for us to think about as we start navigating and working through those limits. But the big idea behind a limit is just understanding that it's a way of describing the y value of a function at a given x value. Now, we talked about earlier that one of the conditions for a limit existing is that we need to be approaching the same value from both the left and the right-hand side. So this is a good segue into discussion of non-existence of limits. Well, when does a limit not exist? Well, we can say the limit when we are approaching our c value from one side, when we don't get the same value as we approach that same c value from the right side. When this happens, we say that this limit does not exist because we're describing what are called one-sided limits. And those are effectively just limits as you approach x from both sides. Oh, excuse me, from one side. I apologize, from one side. Right? So we can say here that the limit as x approaches c from the right and that's the notation here to indicate that we're approaching from the right-hand side, is some limit, and we call this a right-handed limit. And as we approach that same c value, this time from the left side, and that negative there is not an exponent, but just to indicate that we're approaching from the left side, we call this a left-handed limit. So when these two values don't agree with one another, or they're not the same, we say that this limit then does not exist. I would ask you now to pause and think about what are some other instances that I know of where a limit may not exist. If you've taken a previous calculus course or even pre-calc had this discussion, you know that a limit also doesn't exist when our function approaches either positive or negative infinity. That is to say, our limit cannot be infinity. All right, and we'll see an example of this in a bit. And finally, and this is a little less common, but when our function is oscillating back and forth between two fixed values, right? So oscillating functions, we would say, would not have a limit. And I'll show you an example of that a little bit later in the lesson. So as we go through this, we're not going to go through every single problem here, but just something to give you a quick sense of how to find limits and how we can use these limits to define our sense of continuity. So let's take a look at this graph here. Let's kind of focus in on this. And we're just going to graphically use the graph that we're provided to just find the limits at specific x values. So if you'd like, try to pause the video right now and see if you can go through and find these values. All right, so now that you've had a chance to look at it, we can say, what is a limit as x approaches 4? Well, as x approaches 4, let me just highlight this. As x approaches 4 here, and I apologize, my graph is off a little bit. I'm just going to kind of fix this here. I'm trying to make it look like it's going through that -2 because that's what I'm trying to get at. It looks like our function should be approaching -2. And it looks like we're approaching the same value from the left and the right. Well, what about at x is equal to -1? Well, at -1, we've got a little bit of an issue here. It seems as if our function is approaching 4, and that is indeed the limit. However, what about this hole here? Well, that's simply the value of the function at -1. So part E, f of -1 is equal to 1. However, that has no bearing on what the actual limit is. Remember, the definition of a limit is simply describing the behavior of the function, what we are approaching. It has nothing to do often with what the actual output of the function is at that x value. As we move on, what about when x is approaching +3? Well, here at +3, we see a vertical asymptote here. And the issue here is as we approach 3, from both directions, our function is approaching -infinity. So therefore, since our function's limit cannot be -infinity, we would say that this function does not have a limit. The limit does not exist. Now, quick caveat to that. We'll talk about this a little bit more later in the course, but when we are describing one-sided limits, you are then allowed to use positive and negative infinity with the implication and understanding that the limit doesn't exist, but you can use positive and negative infinity there. Moving on, as x approaches +2, we see that our limit would be +1. As x approaches 5, we see that the limit as x approaches 5 is from the left side. So let me just highlight this. This here is not approaching the same value from this direction. They're not agreeing with one another. So therefore, the limit does not exist. We see that the left-handed limit is equal to the left-handed limit is -1, but the right-handed limit is +2. So those one-sided limits do exist, but the limit as x approaches 5 does not because they don't agree with one another. We're also going to be using our graphing calculators at times. I don't have the ability right now to show my graphing calculator, but just like we discussed above, you can often use a graph or just simply use the value feature in your calculator, or even plug in numbers to get a sense of your limits. So just to quickly jot down the answers. Graphically, if you take a moment to look through your graphing calculator and find these values, you should be able to find the limits doing that. Now that we've talked about a limit, let's use our understanding of a limit to describe continuity. Now, you've probably heard the term continuous or have described a function as being continuous in the past before. And we've used some informal definitions. We might say something like, hey, if you can draw the function without ever lifting your pencil, then we have a continuous function. But if you ever have to lift your pencil in order to graph this function, then this function is no longer continuous. And that's fine. It worked well enough for what we had to do in the past. But let's try to have a more formal definition. And the way I break it down is the following. I like to say that the definition of continuity really has three parts, three things that need to be true. First, f of c must be continuous, or I should say f of c is defined. That's a better way of saying it. So the function is defined at that c value. Secondly, not only must that function be defined, and let me zoom in here to have a little more space. Not only must the function be defined there, but the limit must also exist there at c. And then finally, the third condition for continuity is that that limit must be equal to the defined value of the function at c. So, to recap, the function must be defined at c, the limit must exist at c, and on top of that, those two values must be equal to one another. If any one of these conditions are not met, then we would say that the function is not continuous at that value c. And then more formally, if these conditions are met for every x value for which the function is defined, then we say that the function is continuous. Okay? So if all three of these conditions are met everywhere, then the function is continuous everywhere. So really quickly, let me just try one or two of these problems. Let's actually jump to number 6, for example. Let's try number 6. What we're going to do here is we're going to see, are these functions continuous? And if they're not continuous, we're going to state the intervals. Actually, you know what? Let's hold off on that. Let's just make sure we understand why the function is not continuous there. So this function, we will see this time and time again. But for this function here, can we think of a place where this function may not be continuous? And if you said it is not continuous at x is equal to 0, you would absolutely be correct, because if you try plugging in 0 into this function, we see that we have a discontinuity there. So it's not continuous. Because it's not continuous at, we should say it's not continuous at x equals c. Well, why not? Because f of 0 is undefined. As soon as we have some place where the function is not defined, this first condition that we described earlier has not been met. So I'm going to let you pause the video and think about these three here and see whether or not they are continuous. Well, if you've come back, hopefully you've seen that all three of these functions are discontinuous because we have certain values where the function are not defined. In number 5, it's not defined at 5. At number 7, we're not defined at x is equal to 3 and negative 3. Let's get a little bit more particular and specific, though, with continuity. Let's talk about now types of discontinuity. Well, the first type of a discontinuity is something that we call a hole. And we've already seen one of these in the graph above. But we call this here a removable discontinuity. And I guess one way of informally thinking about it is we say that it's a removable discontinuity because if you just plugged in the point that seems to have been plucked out, now that function would be continuous again. Now, if we go to another type of function, suppose we had something that looked like this. It looks like there's a hole there, but now it's going to continue on like this. And we've seen this in the previous example. This is known as a jump step, but more importantly, this is known as what we call a non-removable discontinuity. Because you can't just plug in a certain point and have it be continuous again. There's a whole lot of things that are missing. The gap between these two parts of the function or pieces of the function is too large. So we call this a non-removable discontinuity. The same deal goes for something like a vertical asymptote. If you have a function here that looks like it's approaching positive infinity, for example, and it's also approaching positive infinity, we would say here that you can't just plug in a single point. This function is also going to be non-removable there. And then finally would be something like an oscillating function, which I mentioned earlier. And a good example of an oscillating function would be something like the sine of 1 over x. Because if you really think about what's happening here, as x approaches 0, as we approach 0, what's going to happen is it's going to actually oscillate more rapidly. And if you think about that for a second, as we get closer and closer to x being 0, what we're seeing that is this argument here is going to start to approach infinity. Well, think about that for a second. If you divide by a very small value, you're going to get a very larger valued number. And what do we know about sine? As x approaches infinity, our output is going to continue to oscillate between between -1 and 1. So it's actually a very cool function. The closer you get to 0 here, the more and more this function oscillates. But the bottom line is that this function also would be considered a non-removable discontinuity. How can we use limits to differentiate removable versus non-removable? We should know that for removable discontinuities, the limit still exists. However, for non-removable discontinuities, we would say the limit does not exist. I'm just going to write DNE for short. Okay. So when I ask you to describe whether or not the type of discontinuity, I'm not necessarily asking you to write something like vertical asymptote. I can graphically see often that something is a vertical asymptote. What I want to make sure is that you understand what type of discontinuity it is. So for example, something like number 8 here, I would say, okay, here we see x equals 5 is what we call a non-removable discontinuity. Specifically, we have a vertical asymptote there. We know that a vertical asymptote is non-removable because I just told you that. However, how can we use limits to describe what type of non-removable discontinuity that is? We would say the following. We would say the limit as x approaches 5 from the left-hand side is actually not equal to the limit as x approaches 5 from the right-hand side. Because these limits don't agree with one another, this limit does not exist. Therefore, this is now qualified as a non-removable discontinuity. So I go ahead and encourage you to pause the video right now and try these, and then you can check your solutions with what I have uploaded to my website. All right, last bit of information before we wrap up this rather long and lengthy introductory lesson is just making sure that we understand types of functions that are always continuous. We should understand that polynomial functions are always going to be continuous because their domain, the domain of a polynomial function, is all real numbers. It is going to be defined for every real number. Trigonometric functions, it's important to note that they are always going to be continuous only over their domains. Well, for sine and cosine, the domain of sine and cosine is all real numbers as well. Behaves pretty similarly to the polynomial function in that regard. But for the other ones, the reciprocal trig functions like cosecant and secant and tangent, those are going to have some domain restrictions, specifically some vertical asymptotes. So you'll definitely want to review that, and you can watch my pre-calc lessons on those if you'd like. And then finally, rational functions. Again, over their domain. So something like f of x is equal to the square root of x, making sure that we only understand that over its domain, that function is going to be continuous because it is always going to be defined at every point on its domain, and the limit will always exist there. And to wrap up this box, there is an additional definition of continuity. It's not anything too major, but just know that we can also use our definition of one-sided limits. Specifically, we can say that the function f of x is continuous on the closed interval, and let's say that interval is marked as AB, if the following two conditions are met. If 1, f of x exists for all values, in that open interval AB, and B, the limit of this function as x approaches c is equal to c. Well, this looks pretty similar to what we had already described earlier. What's implied here let me just finish writing this out. What's implied here is understanding that this limit can only exist if the one-sided limits are equal to one another. So again, the limit exists at every point because the one-sided limits are equal, and they are equal to f of c. So it's just a way of just incorporating our definition of limit existence using one-sided limits into our definition of continuity. Well, I know it was a bit of a lengthy lesson, but hopefully we're now getting back into remembering and understanding what a limit is, when a limit does exist, and how we can use that definition of a limit to define our sense of continuity.